We are up to Wednesday, August 3rd for Math 1325. And we're going to be covering sections 5.3 and 5.4 today. 5.3, got 24 problems. Okay, we start off, f of x is 5x to the third minus 4x squared plus 3x plus 8. Find f double prime of x, that's the second derivative. And then find f double prime of 0 and f double prime of 6. So 5.3, problem 1, the original function, 5x cubed minus 4x squared plus 3x plus 8. So we do the first derivative with just term by term power rule. 3 times 5, 15. Decrease the exponent by 1, 2. Minus 4 times 2 is 8. X to the first power. The derivative of 3x is 3, and the derivative of 8 is nothing. This is the first derivative. If you take a derivative of a derivative, that's the second derivative. 15 times 2 is 30, x to the first, and then the derivative of 8x is 8, derivative of 3 is nothing. So first, just in general, what does the second derivative equal? It's 30x minus 8. So that's not any different than what you already know. You just may not have known that you could do it more than once. 30x minus 8. Then we can just plug values into that. In fact, it's going to be helpful when we're looking for our max and mins in a minute here. Plug a 0 in, and you get 0 minus 8 is negative 8. Plug a 6 in. 6 times 30 is 180. Minus 8 is 172. And later, we're only going to care if these answers are positive or negative. Okay, same deal. We can skip that one. Pretty much the same. So this one's pretty quick. 8x minus 4. 8x minus 4 would be the first derivative. 8x minus 4, and the derivative of that's just 8. So the second derivative can just be a constant. So then no matter what number you're plugging in, the answer is just automatically 8. Okay, so what if I have to apply some other rules, though? Now I have x squared over 2 plus x as the original function. X squared over 2 plus x. So the first derivative is the quotient rule. Second times the derivative of the first. The derivative of 2x squared is 2x. Minus the first times the derivative of the second, which would be this 1 right here from the linear part, over the second squared. So this would make a 4x and a 2x squared. And this is just minus x squared. So I can clean this up a little because it'll make the second derivative easier. 2x squared minus x squared is x squared plus 4x. That's all that happened in the top. And then if you want to flip-flop 2 plus x to x plus 2, that's fine. So there's the first derivative simplified as much as possible. So the second derivative, just got to repeat it again. So now I'm going to do the quotient rule again. Second times the derivative of the first. The derivative of first, the power rule term by term. So 2x plus 4 minus the first and times the derivative of the second. And this is basically a chain rule. You'd do the outside first, 2 times the base to the first power. That's the outside part. And then you do the derivative of the inside, except that that would be a derivative of 1, but technically the chain rule is happening there. And then if you square the denominator that's already a square, the square of a square is a fourth power. So again, how much they want this cleaned up is a good question. Maybe they would take this answer, and then we're going to be plugging values into it. Might make it difficult, but another thing you could do is, in theory, you could square this out and FOIL it to that and FOIL these two and then put like terms together. Another thing that helps sometimes is if you pull out GCFs, there's a x plus 2 squared here, and then there's just an x plus 2 to the first power here. So both terms across the minus have an x plus 2. There's a 2 here, and then these two have a GCF of 2 as well. So the GCF part, if you want to simplify this, is, oops, there's a 2 and there's an x plus 2 that you could factor out. So I took the 2 out of this. I took one of these x plus 2's away. So there would be an x plus 2 here and another x plus 2 from this part. So you would still have an x plus 2 squared out of that. So that was actually x plus 2 to the third power at first. But only one of them is a GCF. And then we took the 2 and the x plus 2 away, but we still have this part, x squared plus 4x. All over x plus 2 to the fourth power. And see, this is where it actually helps to simplify, because this 1 out here that's multiplied, that one can cancel one of these 4. So then we're left with just 3 of them. I'm not sure if this simplifying this would help. It might actually. So I'm going to put the 2 down. This binomial squared is x squared. Remember, you multiply this and double it, 4x. And then square the 2 and get 4. And then this would be a negative x squared and a negative 4x. Well, this actually is helping a lot, because now this can cancel that and this can cancel this, which doesn't always happen. So we get a really nice numerator. The numerator is literally just 2 times 4. And then the denominator is x plus 2 to the third power. So maybe they would have taken the unsimplified version like they did a few sections ago, but it would be hard to plug numbers into that big messy thing. So this definitely should have helped. So I got a fraction with 8 over x plus 2 to the third power. Whoops. See, now plugging 0 is really easy. 0 plus 2 is 2. 2 cubed is 8. 8 divided by 8 is 1. And plug 9 in. 9 plus 2 is 11. 11 to the third power is 1331. And that should not reduce with 8 because 8's an even number and this is odd. 8 only divides by 2, 4, and 8, and this shouldn't divide by any of those. So it'll just, you just leave it then 8 over 1331. Okay, so that was implying the quotient rule. Here's one where you can apply the chain rule. So, what number was that? I took a couple of boards of fish. That was 4. Okay, so 5. Now we got square root of x squared plus 49. And I would rewrite that as x squared plus 49 to the 1/2 power. Our square root is a 1/2 exponent. So the first derivative, chain rule, you do the 1/2 times the base, decrease the exponent by 1, which would make it negative 1/2, times the derivative of the inside, which would be 2x. And this 2 can cancel that 2. You could put the negative 1/2 in the bottom, the x would stay in the top. And then you could have x squared plus 49 in the bottom with a positive 1/2. And then you could change it even back to a radical if you wanted to. Although maybe I shouldn't because we need to do another derivative of it. So there's the first derivative, as simplified as possible. So then the second derivative is the second, and let me write it with a 1/2, second times the derivative of the first, which would just be 1, minus the first, and the derivative of the second is literally what we did right here. It's this all over again. So that would simplify to this actually. So you could just put that. Let me put it with a 1/2 though again. So then this x could cancel that one. So I've got and now we can write it as a square root. X squared plus 49 square root, that's the whole first part, times 1, minus, now if the top of a fraction's blank, you have to put a 1 over, and then put this back as a square root. And I don't know if they want you to make that all into one fraction or not, but we can try putting this in. So square root of x squared plus 49 minus 1 over square root x squared plus 49. Okay, so something is off. Sometimes those, when you get it wrong, it doesn't help to, that sometimes the part in that paragraph helps, but that was just generically, no, it's just wrong. Okay, so first derivative again was chain rule, x, and that. The 2's cancel, can't do anything else. Okay, the derivative of this is definitely quotient, so second, derivative of the first minus first, the derivative of the second is the same as this, so it should have the same answer. 1 over that square root, and we got this square root. Okay, so if I get a common denominator, I would multiply this by the square root over itself. That way they're going to both have that in the denominator. And this is kind of nice, but if you ever do a radical times itself, it just equals the inside stuff. So I would have x squared plus 49 over the radical of that minus 1 over that radical. So then you can come all into one common denominator. And then you could actually combine this and get x squared. 49 minus 1 is 48. So that's combining it into one fraction. They might not like this having two separate parts, so. Okay, so the top would be x squared plus 48. And then the bottom is just the radical. X squared plus 49. What I have, yeah. Nope, okay, so there is something wrong here. Let me see what, I made some mistake, but there's the first derivative, I had that. 3/2, okay. 121, so something's happened between the first and the second derivative. Oh, I'm forgetting the squaring the denominator, that's what it is, okay. So, yeah, that's what I forgot. So I did for a second times derivative of the first minus first times derivative of the second. I forgot to do over the second squared. That's what I'm missing, that part. So this should all be fine what I have here, but it would be over the second squared. So then it's over, this is just the numerator part. This is second times derivative of the first minus first times derivative of the second, but then we forgot second squared. So the second squared, that's just going to take the radical away. So you're going to have a fraction inside of a fraction. Fraction divided by a fraction. And then this would just be x squared plus 49 over 1 in essence. So then I could flip the second and multiply. And then since these two parts are the same, this one's to the first power, and this one's in essence to the 1/2 power. And a 1/2 plus a 1 is 3/2. 1/2 plus 2/2 is 3/2. So the final denominator is x squared plus 49 to the 3/2 power. And then the numerator is just times 1, so although the example they did only had a number in it, mine's got an x squared. So x squared plus 48 over that x squared plus 49 to the 3/2. So that's, I think all I was missing was that this should be 3/2, not 1/2. To the 3/2 power. Yeah, see, it's just a 49 somehow. Okay. So where did my x squared come from? But okay, let's go back. X squared so when I had this part should have been over x squared minus or plus 49. That's what I was missing, was I didn't do the second squared. So the second squared is just, the radical goes away, x squared plus 49. So would you have to get that common denominator? 49. Okay, so then it's kind of a mess at that point. If I should still be able to put this together like I did. I don't see how that x squared would go away. Okay, x squared plus 49. Second times derivative of the first minus first times derivative of the second. Those cancel. Square root of 49. That is weird. I'm not sure where this x squared would, how that would go away at any point. Okay, so let me back up here. So I had square root of x squared plus 49 over 1 minus 1 over that square root and then the whole denominator would just be x squared plus 49. So if you flip this and do that to the top and bottom, whoops, 49. This is how you lose all this. So you don't have fractions inside of fractions anymore. Distributing this, that's going to create, so doing this to the one, let me put it as 1/2. So you would have a x squared plus 49 to the 1/2. That would be this. And then this would slide in underneath it and be x squared plus 49 to the first power, which is 2/2. And then here you would get a 1 over, and then this would be a 1/2. And this one, since its first power is in essence 2/2. So that part would get you your 3/2 already. So you could simplify this with the rules of exponents, and it would become 1 over x squared plus 49 to the 1/2, because I'm doing 1/2 minus 2/2 is negative 1/2, or just a positive 1/2 in the bottom. And then we would need to get a common denominator lastly. This one's 3/2. So then x squared plus 49, x squared, I'm still going to get an x squared out of that. I don't see how the x squared goes away. Because I could multiply top and bottom of this by x squared plus 49. But then there would be an x squared up here. X squared plus 40, I'm going to get the same answer doing this. So either there's, let me just take a look at this and let you know what happened here, because I don't want to waste too much of the video trying to, there must be one little mistake I'm making in here somewhere. And this is very common where if you make a little mistake and don't see it, then it's really hard to find it yourself. Finding that mistake, that still didn't get it all the way to the answer. So I'm getting x squared plus 48, but it's just 49 there. So somehow that x squared is a 1. Okay, but then now the easy part is plug the number in. 0 squared is 0. 0 plus 49 is 49. If you're doing the 49 to the 3 halves, let me show you that. Maybe you don't remember that from another class. 49 to the 3 halves is the square root of 49 cubed, which is 7 cubed, because you can do the square root of 49 first. That's 343 for the denominator part. And the top is 49. So plugging in f double prime of 0 gives you 49 over 343. And these both divide by 49. Does 4? They both divide by 7. Does this divide by 49? Yeah. So they both divide by 49. That makes it 1 over 7. 1 over 7. Whoops. 1 over 7. And then plugging in a 9. 9 squared is 81. 81 plus 49 is 130. So that's not going to come out as a radical. Type in integer or a decimal. Okay, so apparently they want a decimal for that one because it doesn't come out evenly. So 9 squared is 81. 81 plus 49 is 130. The square root of that doesn't come out evenly, but we'll do a decimal then. Raise it to the 3rd power, another decimal. And then finally it's 49 divided by this. And round to 2 decimals. So 0.03. Okay, so yeah, something's going weird on that problem. The numerator, I can't get that numerator to come out somehow. Okay, so exponentials. This is number 6. F of x is 4e to the negative x to the 4th. 4e to the negative x to the 4th. So first derivative, remember the main rule about exponentials is you first write it down exactly as it is, and then it gets multiplied by ln of the base, but that's the nice one when it's ln of e. And then you have to multiply by the derivative of the exponent because that's the chain rule. So times negative 4x to the 3rd. And ln of e equals 1, so that'll go away. I've got a 4 and a negative 4, so you usually put the constant first. There's an x to the 3rd that would go next, and then you put your exponential in the back usually. So that's not too bad there because it's just a chain rule. But then when I switch to the second derivative, now there's 2 different functions of x multiplied together. That's product rule. So first, times derivative of the second. So that's this all over again. So first I write it down exactly as it is. Times ln of e, which I'll skip. Times the derivative of the exponent, which is negative 4x to the 3rd. first times derivative of the second plus the second, which is just that part, times the derivative of the first, which is negative 48x squared, using the power rule. Okay, so try to get GCF stuff out to the front. They both have an e to the x to the negative 4. They both have at least 2 x's. This one's actually got 6 x's. And then 16 times 4 is 64. 48, they can both divide by 16. So, and they're both negative too. So if you want a GCF, negative 16 x squared e to the negative x to the 4th. And that would leave, there's 1x here and 3 more there, x to the 4th, and there's also this negative 4. And then I took the e to the negative x out. I took both x squareds out, and I took negative 16 out. So there would be a positive 3, and that should be it. Negative 4x to the 4th. Yeah, this is a 4. I couldn't read what I wrote there. 4. Okay, so negative 16 x squared e to the negative x to the 4th, the exponent inside of an exponent. That's the GCF. And then negative 4x to the 4th plus 3. Okay. Plug in 0, so this will be nice because this will be 0 right here. Anything times 0 is 0, so all of this equals 0. And this part will be 0. But 0 plus 3 is 3. 3 times 0 is 0. So the whole thing should just be 0. Now plugging a 1 in, do they want a decimal? Yeah, see, they want a decimal here. I could tell they were going to do that because when you plug a 1 in here, you're going to get an e to the negative 1, which is not anything nice unless you just want to leave e in it. So put a 1 in, that'll make this be 1 squared times negative 16 is negative 16. 1 to the 4th is 1, so you'll get e to the negative 1. So that part will be negative 16e to the negative 1. Let's do it over here. So negative 16, 1 squared will eventually disappear. E to the negative 1 to the 4th, but that's negative 1. And then negative 4 times 1 to the 4th plus 3. So negative 16, 1 squared doesn't matter. You would do the 4th power first. You'd do 1 to the 4th, which is 1, and then it would be e to the negative 1. And this 1 to the 4th is 1, times negative 4 is negative 4, plus 3 is negative 1. So you could do your negative 1 times your negative 16 and get 16. And e to the negative 1 could drop to the denominator and be e to the positive 1. So it's just 16 divided by e. If that would actually be the exact answer. They sometimes ask for that. 16 divided by e. Round to 2 decimals? No, 4 decimals. Whoa. So 5.88607. You got to add 1 to the 0 and make it a 1. 5.8861. Okay, similar deal, just quotient rule, and then you'll have to do the ln, the natural log derivative. This is different. We better do this one. Okay, number 8. So the original function is 4x to the 5th minus 4x to the 4th plus 3x to the 3rd plus 6x squared plus 5. So you've already seen you can do the first derivative. That's just term by term power rule. 20x to the 4th minus 16x to the 3rd plus 9x squared plus 12x, and the derivative of 5 is nothing. Then you do it again and you get the second derivative. 80x x to the 3rd power minus 48x squared plus 18x plus 12, because that's just the linear part of the constant of the linear part. So the first derivative we work with a lot. Obviously, the second derivative we're going to see some more. And then there is higher derivatives too. So you can do a third derivative. Put 3 little apostrophe marks. So do it again. Now you got 80 times 3, 240 x squared. Notice the exponents are getting smaller and smaller and smaller. 2 times 48 is 96 for x. Then not only are the exponents getting smaller, but the terms start disappearing, because once you reach a constant, that part has no derivative. So the 18x, the derivative, that's 18. If I did another derivative, that part will go away. So the third derivative is 240x to the 3rd. Nope, sorry, x to the 2nd, and then minus 96x plus 18. Plus 18. Third derivative. Then you can do the fourth derivative. Now, they just like with Roman numerals, how they do Roman numerals, you have 1, you have 2, you have 3. Then they don't put 4 marks or 4, they put IV in Roman numerals. If you get too many marks, it's hard to see them all. So instead of putting 4 little apostrophe marks, they just put a 4 in parentheses to mean fourth derivative. So 240 times 2 is 480, x to the 1st, and then the derivative of negative 96x is just negative 96, because then the rest would be 0. 480x minus 96. If you kept going, the fifth derivative would just be 480. And the sixth derivative would be 0, and so would every one after that. Okay, so quotient rule a bunch of times. Let's see what happens here, I guess. Number 9. Original function is x minus 2 over x minus 6. And they want you to go all the way out to the fourth derivative. The one thing that makes this not maybe as bad as it could be is that these are 1x's. So that way, the derivative of each one is just 1 every time. So the first derivative, second, times derivative of the first, which is just a 1, minus the first. Derivative of the second is 1, and then you do have to do over the second squared. And this is nice because the times 1s don't matter, so you get x minus 6 in the top, minus x and plus 2. The x's cancel out. Negative 6 plus 2 is negative 4. So the first derivative is negative 4 over x minus 6 squared. And then you could write that as negative 4 x minus 6 to the negative 2. And that way you don't need to do the quotient rule anymore because this doesn't have an x in it. The numerator, it's not two different x's divided by each other. That's just a constant now. So if there was still an x in the numerator, I would have to do the quotient rule again. And you could actually do the quotient rule on this, and when you get to the derivative of the first, it'll just be 0, and it'll knock that part out. But if you recognize that this x minus 6 squared could be x minus 6 to the negative 2 in the numerator, then it's just a power rule or a chain rule. Less work. So negative 2 times negative 4 is 8. Base stays the same, and then you decrease the exponent by 1 to negative 3, and then technically you multiply by the derivative of the inside, but that's just 1. And that's already simplified. So now these next two are going to go quicker. The third derivative, we don't need this, is negative 3 times 8, negative 24, x minus 6 to the fourth power, negative fourth power, sorry. And this is the first answer that they want, I believe. Negative 24, x minus 6 to the negative 4. And then do it one more time. Negative 4 times negative 24 is positive 96. X minus 6 to the negative 5. And then technically times 1, but that won't matter here. So the first step was quotient rule, but then it got easier after that. Same kind of problem in number 10. Okay, now we got something different. Okay, so it took us 10 questions just to get past all this. So back in the previous sections, when a first derivative is positive, the original graph is increasing. If the first derivative is less than 0, then the original graph is decreasing. And if you change from increasing to decreasing or vice versa at a critical number, then you get a local max or min. Very similar things happen with the second derivative. We're going to look at what makes the second derivative equal 0 first, so that we can find what I guess equate to critical numbers. They just don't call them that. But it's like you're going to find the critical numbers of the second derivative, anything that makes it 0 or undefined. And that way we can search what intervals are those second derivatives greater than 0 or less than 0. And in the sections that are greater than 0, the original graph, not the derivative, but the original graph, is called concave up. Concave up is a curvature like an x squared, like so. That's concave up. If it's less than 0, if it's negative, then the original graph is concave down. Like this. And if you change from concave up to concave down or vice versa, instead of getting a local max or min, you get what's called an inflection point. So if you have a curve that goes like this, that's concave down, and then say right at this point right here is when it starts bending the other way. That's called an inflection point. And we're going to have a concept in a future chapter where that's a key point. If you're a business person and you're advertising your company, and you notice advertising works, because otherwise why would people spend millions of dollars on Super Bowl ads? But there's what's called a point of diminishing returns. If you just keep throwing money at it, at some point then you don't make up, your profits start to suffer from the money that you're spending on advertising. So there's an ideal amount to spend so that you can maximize your profits, and that occurs at an inflection point. It's called the point of diminishing returns, where you're spending more on advertising to increase your profits, but if you spend too much, then they start decreasing. And that's where the curvature changes. So find open intervals where the function's concave up or concave down. This is very similar to before when we were looking for intervals where the graph was increasing and decreasing. So this is this portion of the graph right to that point. They only put 1 point on this whole graph. I guess they did it on purpose to focus your attention to that spot. That whole portion, see how that's curved downward. This is concave down right here. You think about if you used your hand, you'd have to cup your hand downward over that. And then when you go past 3, now all of a sudden it's cupped upward. So this is an inflection point right here. It's concave down from negative infinity until you get to 3. And this time they're going to let me answer the first one that happens instead of doing them in order. So negative infinity to 3, it's concave down. And it, whoops, delete that. And then it's concave up from 3 and ever after. 3 to infinity. And if it changes from down to up or up to down, that is an inflection point. Now, in the first derivative stuff, if it changes from increasing to decreasing, that's a local max. But if it changes from decreasing to increasing, that's a local min. They distinguish those two in the first derivative. In the second derivative, there is no difference. It doesn't matter if it's up first and down second or vice versa. That's just called an inflection point. There's not a separate name for if the order changes. And I don't have to do it much here because they labeled the point already. So sometimes you have to, they give you the X where it's happening and you got to find the Y yourself. But I can just look it up here on the graph. So that was an inflection point there. Okay, so I've got a quadratic here. Three x squared plus 2x minus 7. Okay, so first you find the first derivative, 6x plus 2. Then you find the second derivative, which is just 6. This is greater than 0, it's positive. When the second derivative is positive, the original graph is concave up. And this one would be always concave up because the second derivative is a constant positive 6. That means it's positive 6 for all x. There's never a time that this second derivative equals 0 or is undefined. It doesn't have any what would be called critical numbers. So there's no chance for it to change from concave up to down or vice versa. Whatever it's doing in one place, it's doing the same thing the whole time. And as you know, you probably know that this is a parabola graph. Parabolas look like this. So that makes sense. It's concave up the whole time. So that was kind of a simpler one, but the function is concave up everywhere because the second derivative is positive 6 everywhere. And it won't have an inflection point. It can't have an inflection point unless you switch from concave up to concave down or vice versa, which can't happen if you're always doing the same thing the whole time. Okay, so let's get to maybe a more interesting one. I want to get to a higher power. There, this is probably better here. Number 16. So now we have a cubic original function. 3x cubed minus 6x squared plus 3. So I can do the first derivative easily. 9x squared minus 12x. That's the first derivative. Set this equal to 0. And then I could factor out a 3x, leaving a 3x minus 4. This is going to equal 0 twice. It's never undefined because it's a polynomial. So it's equal to 0 at 0 itself. And if you add 4 and divide by 3, 4/3. So there's two critical numbers. If you want to do the first derivative test, first derivative test is what we did last time. You use the critical numbers and you have to pick a checkpoint in less than 0, between 0 and 4/3, and bigger than 4/3. But in order to tell if 0 is a max or min, you have to use both the -1 and the 1. You have to plug them into the first derivative. And you hope 1 is positive and 1 is negative, then you have a max or a min there. So it takes two calculations to figure that out. You have to do f prime of -1 and f prime of 1 to be able to tell what's happening at 0. And then you have to do 2 for 4/3 as well, but one nice thing is you can reuse the 1, so you don't have to do that all over again. You just reuse that one, but then you have to do this one too. So the first derivative test takes a little longer because you have to do 2 calculations for each spot in essence. If finding the second derivative isn't too hard, like this problem, then it's less work to do the second derivative test. Now, if the second derivative is going to be a messy quotient rule like that one that I couldn't even figure out, then you're better off just sticking with the first derivative test. But this is a simple enough one to get 18x minus 12. I could get the second derivative in a matter of seconds. So then it turns out if you plug the critical numbers of the first derivative, don't find when this equals 0, that would just tell you when the concavity changes. But if you plug in these critical numbers that came from the first derivative into the second derivative, in one calculation, you'll know if there's a max or a min. That's called the second derivative test. Second derivative test. So f double prime of 0 would be -12. Because I'm at a critical number of the first derivative, that's a spot. If it came from a 0, that's a spot on the original graph that's flat. I have a flat portion of the graph. Now maybe the graph increases, it's flat right there, and then increases again after that. That's possible. Or maybe it increases, it's flat, and it goes down, and then I got a maximum. So you can't tell that instantly, but the one thing you know is it's flat right at that spot. And if it's flat at 0, at x of 0, and it has a negative second derivative, that tells me it's concave down at that spot. Now, it may not be an inflection point for concave down, and it may not be there may be concave down all around it, or maybe it changes soon after, but the point is you're at a spot on the original graph that's flat, and it's concave down there. So it has to bend downward and be flat at that spot, which means it has to be a maximum. We can immediately tell that it has to be a maximum, because if it kept going up, it wouldn't be concave down. So that's what's nice, is the second derivative will tell you in one calculation if you plug in a critical number from the first derivative into the second derivative and it's concave down by being negative, then you immediately know there's a local maximum there. There's a local maximum at x equals 0. Now, I don't know what the of part is, but if they ask for that, then you always go back to the original for that. So actually, the of is right there of 3. There's a local maximum of 3 at x equals 0 because I can easily plug 0 into the original. And then if I do the second derivative at 4/3, 18 times 4/3 minus 12. 18 times 4/3 minus 12 is 12. So this is positive. If you're positive at a spot where you know it's flat on the original graph, then it has to be concave up there too. So a flat portion of the graph that's concave up exactly at that spot, that has to be a local minimum. And you can memorize it, but I just draw a quick sketch of what's happening, and it's obvious if that's a max or a min. So two downsides to the second derivative test is if finding the second derivative is going to take a long time, then it may not be worth the effort. And secondly, if this calculation is 0, which it could be, if this second derivative, plugging in a critical number from the first derivative, you plug that into the second derivative, you might get 0 for an answer. If it's 0, then the test is inconclusive and you'd have to go back and do the first derivative test anyway. And you might be thinking, okay, why don't I just do the first derivative test every time? That works every time. It does, but if the second derivative test is easy, if the second derivative is easy to find, then, and especially if there's a number of critical numbers, say you have 4 or 5 of them, then it's definitely easier to do the second derivative test. And you just hope that you don't get any 0 ones that are inconclusive. So let's see what they want for answers here. There's 2 critical numbers of the original function that came from when the derivative was 0. 0 and 4/3 were the 2 critical numbers. At the smaller number 0, I could have done the first derivative test to check for this, but the second derivative test told me because it was concave down there, there's a local maximum there. So there's a local maximum at the smaller critical number. And apparently they're not saying the of and the at, or okay. So then there's a minimum at the other one. And they didn't care about the ats and the ofs. So that's how you do the second derivative test. And then maybe we'll do one of these here. See, here's what I was talking about. Find the point of diminishing returns. This is a good example. We're almost over an hour at this point though, but let's just do one more from this section. So the original revenue, this is a revenue function, how much money the company's taken in. So the revenue function is negative 0.2 x to the third plus 3.3 x squared and plus 7x. So I get the first derivative. 3 times negative 0.2 is negative 0.6 x squared. 3.3 times 2 is 6.6 x, and then that's 7. So this could have 2 critical numbers. Here's a trick. Since there's 1 decimal place on each of these, you can, after you set this equal to 0, you can multiply everything by 10 and it'll get rid of the decimals. Whoops. So negative 6x squared, or we can even do negative 10, so this comes out to be positive, and then negative 66x and negative 70. and anything times 0 is 0, so that doesn't change. These definitely all divide by 2, so 3x squared minus 33x minus 35. Okay, so then 7 times 321, and 5 wouldn't work. 35, 7 and 5. So maybe I was thinking maybe this might factor, but it looks like it doesn't, so we might get stuck with the quadratic formula. One way we could tell is how do they want the answers? Do they want decimals? Yeah, see how they want decimals? So that's usually a sign that it's not going to come out exactly. Okay, so opposite of b, plus and minus, square root, b squared minus 4 times a times c all over 2a. Okay. I'm going to do negative 33 squared, or just 33 squared because a negative squared is also positive, minus 4 times 3 times negative 35. The inside of the radical is 1509, and that probably doesn't come out exactly as a square root. No, it does not. So I did the inside of the square root and then square rooted it. And then we can do 33 plus that and 33 minus that over 6. So 33 plus this answer divided by 6. The first x, and how far do they want it rounded? Do not round to the final answer, then round to 2 decimals. Okay, do not round to the final answer. So 1x is 11.97438082. That's one critical number. So then if I do 33 minus 38.845892. Oops. Didn't get point. Okay. And then divided by 6. The other one is negative 0.97438082. Except we're in a business setting where things probably can't be negative. What's X? X represents the amount of money spent on advertising in thousands of dollars. You can't spend negative amounts of money, so this one gets crossed out, luckily. Okay, so then I can do the second derivative pretty quickly from the first derivative. The second derivative would be 2 times negative 0.6, negative 1.2, x to the first power, plus 6.6. It was pretty easy to do the second derivative. And then if I plug in, well, I'm doing the wrong kind of problem. So I was going to plug this into the second derivative, and that would tell you if it's a local max or min, but they're actually looking for the point of diminishing return. So that would be, so actually I did all this for nothing. That would be, now what we do for that is we're looking for an inflection point. An inflection point is a possible point of diminishing returns. So I should have, after I got my first derivative, I didn't even need the critical number so much. We could have went right to the second derivative and gotten negative 1.2x plus 6.6. So there's a difference between finding local maxes and mins with the second derivative. That's called the second derivative test. If I'm ignoring maxes and mins, then setting the second derivative equal to 0 these are not called critical numbers, but in essence, it's like the critical numbers of the second derivative. So negative 1.2x equals negative 6.6. Divide by negative 1.2. Oops. So that is 5.5 exactly. So 5.5 may be a point of inflection, which would be a point of diminishing returns here. So this is what happens is you treat this like you're doing the increasing and decreasing of the first derivative. You make a number line and put what would be like a critical number on it. I only have one. And then I can check one number below that and one number above that into the second derivative. The second derivative of 0 would be 6.6. So that's positive. If I plug 6 in, negative 1.2 times 6 plus 6.6 is negative 0.6. Okay, so the second derivative is positive all the way until you get to 5.5. So that's when it's concave up, an upward curvature. And then exactly at that spot, it switches to negative for its concavity, so then it's concave down. This is an inflection point because it switched from positive, negative, or the other way around. The order doesn't matter here. So therefore is the point of diminishing returns. So the company, their profits are increasing well by spending more, but then if they keep spending more, now they don't increase as fast. It can still be taking money in, but you're not taking in a maximum amount of money. So at x equals 5.5, that is a point of diminishing returns. Now the fact that it's a point of diminishing returns means they might want me to find the y value of it. See, type an ordered pair. X is in thousands of dollars, so we're talking $5,500, but I think they just want you to put 5.5 still, and it would be converted to thousands later. So to get the y value, anytime you need a y value to any of these answers, it always comes from plugging it back in the original. So if I do negative 0.2 times 5.5 raised to the third power, and then plus 3.3 times 5.5 squared plus 7 times 5.5. 105.05. No rounding. So if they spend $5.5 thousand, which is really $5,500, if they spend that many thousands of dollars on advertising, their revenue will hit a maximum possibility of 105.5 thousands of dollars. So in other words, that would be over $1 million. So then they know their ideal amount to spend on advertising. That'll maximize their profits. So that's one key concept in this section 5.3 is that point of diminishing returns. And then most of the problems in 5.4 are similar. 5.4, it's only 10 problems here. You're basically putting everything together that you've learned in this chapter up to this point to help you sketch a graph. And the graphs here are multiple choice, which helps. So here's a good typical problem. Number 1 of 5.4. And some of these more basic ones, you might have college algebra knowledge of what the graph's doing anyway. But let's go through the calculus side of this. So negative 4x to the third minus 12x squared plus 96x minus 14. Find the first derivative. Negative 12x squared minus 24x plus 96. This is a polynomial, so it's never undefined. It could be 0 up to 2 times. There could be 2 critical numbers. I would try dividing everything by negative 12 if you can get away with that, because then you'll have a nice 1x squared. It'll be easier to factor. Negative 24 divided by negative 12 is positive 2. 96 divided by negative 12 is negative 6. No, negative 8. So this will factor into x plus 4 and x minus 2. Two numbers that multiply to negative 8, and they subtract to give you a positive 2. 4 minus 2 is 2. So I have 2 critical numbers, x equals negative 4 and x equals 2. If I only cared about local maxes and mins, it would be worthwhile to do the second derivative test, because the first derivative is right here. The second derivative isn't too hard from that. The second derivative would be negative 24x minus 24. And if you plug 2 into that, you're definitely going to get a negative answer. So the graph is concave down exactly at 2. It's flat at 2, and it's concave down there. So there's a local maximum at 2. See how quickly I was able to determine that? If I wanted to do the first derivative test, I would have needed 2 calculations to figure that out. I'd have to pick something a little bigger than 2 and something a little less than 2. And I would have to hope one was positive and one was negative to know that that's a local maximum. And if I plug negative 4 in, negative 4 times negative 24 is positive 96. Minus 24 is definitely positive. So at negative 4, it's flat again, but it's concave up in that location. So there must be a local minimum here. So the second derivative test told me each one of those in 1 calculation each. Now, I'm doing everything on this problem anyway, so I didn't have to do that right now, because we're going to be forced to, in essence, do the first derivative test anyway, because we need to know when the graph's increasing and decreasing, and only the first derivative can tell you that. So I'm going to put negative 4 and positive 2 on a number line anyway, as if I was doing the first derivative test. And then I need to pick, say, negative 5, 0, and 3, and plug them into the first derivative to see if they're positive or negative. And I need this to know if the graph's increasing or decreasing, but then it'll also tell me the maxes and mins as well. I should be able to confirm it at least. So plug negative 5 into here. Negative 12 times negative 5 squared minus 24 times negative 5 plus 96. So I'm plugging negative 5 into the first derivative. It's negative 84. So more importantly, it's negative. When the first derivative is negative, that's when the original graph is decreasing. And then the first derivative of 0 is easy because all the x parts will disappear. So that's positive 96. It's positive in this region. So now the graph is increasing between negative 4 and 2. If you decrease first and then increase second after a critical number, that has to be a local minimum. So there's a local minimum at negative 4. Did we say that over here? Yep, local minimum at negative 4. But it took me 2 calculations to determine that here. This was the first derivative test. So the first derivative test, second derivative test, they tell you exactly the same thing. And if you only care about local maxes and mins, you could choose which one you want to do. The reason I'm doing both of them here is because this problem wants to know everything about the chapter. When are things increasing and decreasing? Where are the maxes and mins? Are there any inflection points? When is it concave up and concave down? We're in essence doing everything in one problem. Okay, so then finally f prime of 3 would be negative 12 times 3 squared minus 24 times 3 plus 96. That's negative 84. So it's back to negative now. Now you get to reuse this positive answer, so you're increasing first, and then it's flat, and then you're decreasing after that. So that is a local maximum at 2. And the graph is decreasing there too. Okay, so then from the second derivative, now we're going to do kind of what we just did on this first derivative. I want to set this equal to 0 and figure out what makes the second derivative equal 0. Add 24, divide by negative 24. The second derivative is 0 one time only at negative 1. So that's kind of like a critical number. We just don't call it that. But put it on a number line and try one number less than that, one number bigger than that into the second derivative. And if this comes out positive or negative, this will tell you if you're concave up or concave down, which is separate from, this has nothing to do with maxes or mins. So plug negative 2 in times negative 24, that's 48. 48 minus 24 is 24. So the second derivative is positive in this region. So that means the original graph is concave up at in that region. And then if you plug 0 in, you obviously get negative 24. It's negative in this region. So then the original graph switches to concave down. And because we switched from up to down exactly at negative 1, negative 1 is the point of inflection. Or not the point of it, but the x part of the point. But there is a point of inflection exactly at negative 1. So then we could sketch a graph of this, and you could get more details too if you found things like x-intercepts and y-intercepts from algebra. College algebra knowledge helps, knowing the end behavior of a graph and zeros of it from college algebra potentially. So I have a point of inflection at negative 1. I've got a local minimum at negative 4 and a local maximum at 2. So I should be able to see all those on the graph. The graph is decreasing from negative infinity to negative 4. It then increases from negative 4 to 2. And then it decreases from 2 to infinity. So I need to check which graph has that. And then not only is there a point of inflection at negative 1, the graph should be concave up at first until I get to negative 1, and then concave down forever after that. So I want to use all that knowledge to figure out which graph it is. And again, college algebra knowledge could help here because there's a negative odd power. So that's one that rises on the left and falls on the right. So it can't be graph A or D. Okay, so here it is. See how this is cupped upward. So it's concave up first, and then it's concave down after that. And it's supposed to change at negative 1. That's a little hard to tell where that's exactly changing at. Is that this is such a small scale here. It's hard to tell where the negative 1 is. So I guess the difference is this right here. Is it that point or is it here? The rest of this, there's not enough detail to really tell what's going on here. The local minimum and the local maximums could help, especially the local maximum. does the local maximum have a y value of 0, or is it some positive value? That would be the best way to tell here. So where was my local maximum? The local maximum occurred at 2. So what's f of 2? What's f of 2 back in the original function? -4 times 2 to the third power, to the third power, minus 12 times 2 squared, plus 96 times 2, minus 14. Is this 0 or is this some positive number? It's a positive number, 90. So it must be this, because see, this goes all the way to 200. So that could be 90, I guess. It's hard to tell because it's so tiny. But it's certainly not 0 or close to 0. So it must be graph C. But the idea is I have concave up until I get to -1, concave down forever after. I'm decreasing until I get to -4, and that's a local minimum. Then I increase till I get to 2, and that's a local maximum. And then I decrease forever after. So that's the idea, is you're putting all this together in one graph. And then there's a point of inflection at -1, although it's hard to tell there. So pretty much similar here and here. Just see if any of these are different, because the directions are the same in all of these. You're just doing all that stuff like checking your domain, critical points, symmetry, when's it increasing, decreasing, inflection points, when's it concave up or down, intercepts, all that helps you to do a graph potentially. Okay, so here's a different kind. So those first 8 are all the same kind. Then the other way they can do this is, rather than give you the function where you can do the derivative yourself, sometimes they just describe in each of these parts what's happening in the graph. And in many textbooks, they make you draw these by hand, but at least here you got multiple choice. So we need to be continuous and differentiable everywhere except x equals 1, where it has a vertical asymptote. In a spot that has a vertical asymptote, the graph won't exist there. So then you can't even do a derivative there either. X equals 1 needs to be a vertical asymptote, which could be graph A, certainly not graph B, could be C, and it could be D. So we've already eliminated graph B from the first condition, that it needs to have a vertical asymptote at x equals 1. The derivative is greater than 0 everywhere it is defined. So if a derivative is greater than 0 everywhere, then it should be increasing everywhere. So notice graph A, how this is going up, 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 up. That is increasing everywhere. Graph C, though, is going down, 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 down. That's decreasing everywhere. And this one's already wrong, too, because it's increasing for half the graph, but it's decreasing for the other half. So from just condition A and B, I already know the answer is A. But we can check the other ones, too. A horizontal asymptote at -2, yes. Its second derivative is positive from -infinity to 1. Positive second derivative means you're concave up. So notice that from -infinity to 1, it's curved upward, concave up. And it's also doing so from 2 to 4. So notice from 2 to 4, it's bent upward too. Then it's concave down between 1 and 2. Right there, it's bent downward, bend, a downward curvature from 1 to 2. And then also from 4 to infinity, it's downward bent. So even though I knew the graph was A, after part A and part B, part C, D, and E all check out on that graph too. Okay, so now this one's continuous and differentiable for all real numbers. So that means if you draw it left to right, you should never have to pick your pencil up. but all of these graphs appear to do that. So I can't eliminate any of them from condition A. We need the first derivative to be positive from negative infinity to negative 5 and from negative 2 to 1. That's when it's increasing. We need to be increasing from negative infinity to negative 5 and from negative 2 to 1. Increasing from negative infinity till negative 5, okay? And negative 2 to 1. Yeah, that one did that. This one's not. This one's decreasing first. Same with that. And here's one that's increasing, but it's not doing it from negative infinity to negative 5. It's going all the way to negative 1. So once again, after condition B, I already know the graph is A. But then we could check these other things, make sure they're true. Is it decreasing from negative 5 to negative 2? Yes. Because when a derivative is less than 0, the original graph is decreasing. Is it decreasing from 1 to infinity? Yes. Is the second derivative, when the second derivative is less than 0, then it's concave down. So is it concave down from negative infinity to negative 3, where it's bent downward? Yeah, see how it doesn't stop bending downward at the maximum? It's still got a downward curvature after that. It doesn't change from cupped down to cupped up until you get to negative 3. So right about there, that's when it stops being curved down and switches to curved up. And it curves up all the way till about there. So was that the other one? Yeah, see, from 0 to infinity. And from negative 3 to 0, it has concave up. From negative 3 to 0, it's concave up, which is not where the local mins and maxes are. Usually the concavity switches at non-max and mins. And then from 0 to infinity, it's concave down again. And then our f prime of negative 5, f prime of 1 equals 0. That's flat points of the graph. When the derivative is 0, you have a flat point on your graph. Negative 5, it's flat. And positive 1, it's flat. Yep. And the second derivative equals 0 at these 2 points. That's when you change from concave up to concave down, potentially. Or if you do switch at those points, then you have an inflection point. So yes, at negative 3, 3, negative 3, 3, which I guess is here, not as far as I thought it was. So right there, that's when it switches from concave down to concave up. So that's an inflection point there. And there's another one at 0, 4 right there. So they're not exactly the same height as each other. So you're doing concave down like that all the way to 3, negative 3, 3. And then from there to 0, 4, then it's concave up. And then it switches back to concave down forever after. So these 2 spots are inflection points. Concave up and concave down there and there. So that was all true on that graph. So there's no business problems here because this is all about graphs. So any of these interesting? That one we've seen already. Okay, this might be an interesting one here. Number 6, we'll do one last problem here. Number 6. Number 6, I've got 4x times e to the x as the original function. So the first derivative is a product rule because I have 2 functions of x multiplied together. First times derivative of the second, the derivative of e to the x is literally e to the x. Because then it's also technically times the ln of e, which is 1, and times the derivative of the exponent, which is 1. since that's a 1x linear part. So that's the nicest exponential. The derivative of e to the x is e to the x. So first times derivative of the second, and the second times the derivative of the first, which is just 4. Okay, so then we'll work with that, but we're going to need the second derivative in a second. And you could try cleaning it up, but there's a GCF of 4 and not much else. Well, 4e to the x. So if I did do that, would that make it better? 4e to the x is a GCF. And then you would have an x plus 1 left over. That might be better to work with for the second derivative. Okay, so second derivative will be first times the derivative of the second, which is 1, plus the second, and the derivative of the first is itself, since it's exponential and it's e to the x. Okay, so this has a GCF of 4e to the x. One plus x plus 1. So that could be x plus 2. So I've got this for the first derivative and this for the second derivative. Okay, so what would make this? This is never undefined because exponentials are never undefined. And this is just a linear piece, so there's nothing that's going to make this undefined. What could make this equal 0 is a question, though. Whenever you have a product equal to 0, you can set each part equal to 0. So I can say 4e to the x equals 0, or x plus 1 equals 0. But e to the x is like this. And it's got a horizontal asymptote of 0. It never touches 0. And multiplying it by 4 just stretches it out vertically times 4. It never equals 0. So you don't have to have 0. You don't have to have critical numbers from every part. This never equals 0, so there's no critical number coming from there. So the only critical number is going to be -1. This is my only place to possibly have a max or min. And I could either check a number less than -1 and bigger than -1 plugged into the first derivative. That would be the first derivative test, and we might need to do that to see increasing and decreasing. We could also plug it into the second derivative. And in one calculation, we would be able to tell if it's a max or a min. Unless it comes out to 0, then it's inconclusive. So plug in -1 for that x right there. Plug it in for this x. This part will be 1. And e to the -1 is just 1 over e, so I could get 4 over e for that. I don't really care what 4 over e equals. The key thing is that it's definitely positive. So we're concave up exactly at a spot where the derivative is 0. That's a flat point on the original graph. See, the original graph has a flat point at -1, and it's concave up there. That is a local minimum. So there's a local minimum at x equals -1. We can also set the second derivative equal to 0 the same way we did the first derivative. And again, the exponential part will never equal 0. So what makes x plus 2 equals 0? That's -2. So -2 now becomes a candidate to be a inflection point, possibly. So then I could try one number on each side of that in the second derivative. Plug in like -3 and 0. 0 is nice because e to the 0 is 1, times 4 is 4, and then 0 plus 2 is 2. So 4 times 2 is 8. It's positive when you plug 0 in. So we're concave up anywhere after -2, and that makes sense because we said it was concave up at -1. So that actually makes sense. And then is it concave down less than that? That's a little harder to tell because plugging -3 in for x, this would be -1 right here. E to the -3, e to the -3 is not even negative, it's just some decimal number, times 4. But then when you plug -3 into x plus 2, you'll get times -1. So it'll just switch the sign. So it is negative. So the graph, the original graph would be concave down from -infinity until you get to -2, and then it's concave up after that, so there is an inflection point at -2. So we can check our graphs and say which graph has a -2 inflection point and which graph has a local minimum at -1. And again, some of these are hard to tell. So this is concave down at first, and then concave up, so that's right. But see, this one's concave up first. Plus, B is out because our key points are -2 and -1. It switches concavity at -2, and there's supposed to be a local minimum at -1. It's switching concavity right there at -2, and then it has a local minimum at -1, so it could be graph A. It's definitely not graph B. The local minimum there is +1. And it's not C because that's a local maximum. And that's a local maximum. So it has to be graph A already. And I probably did more to the problem than needed to figure that out, but that's what you want to be doing in this section basically, is working with your first derivative and your second derivative. The first derivative will tell you when the graph's increasing and decreasing. I didn't even do that for this problem. We could have checked that too. The second derivative will tell you when the graph's concave up and concave down. And then if you get critical numbers from the first derivative, you can plug them into the first or second derivative to try to figure out where local maximum and mins are. Okay, so at least you got a pretty good flavor on 5.3 and 5.4, how they work. I'm still not sure what happened on this problem, so I'll try to research this, and I'll just send out an email and tell you what I found on this. But this one stumped me somehow, and I don't know. I'm making one little mistake somehow. According to them, somehow this x squared is supposed to go away. So I got to figure that out. But other than that, you should be good to go. And then tomorrow you can review, and Friday or tomorrow take the test.